All right, here we are, middle of chapter 9. This is the 9495 FRQ practice with just two FRQs for us. These are both going to get into one sample t-tests for mu. Let's just dig in. We've got the first one, which is about apartments in a new development in Rosemount. They are advertised to be 1,250 square feet. And the advertised means right away they're giving you the claim, right? Which, in other words, this is going to be lower down. This is going to be your null, okay? Keep going. With a standard deviation of 38. Interesting. Okay, so is actually, um, this is actually sigma. They're talking globally about all the apartments. So they actually have the data for every apartment they've built. And they're claiming um, that it has that standard deviation. Okay, a tenant group thinks that the apartments are smaller. Okay, so that's going to be important. They're smaller, so that's going to lead to the alternative hypothesis. They're smaller than advertised, and they took a sample of how many apartments? 150 apartments. That's my N. Okay, and they found an average square footage to be only 1240. Okay, um, what color do I want to use now? I don't know. Orange. So 1240 is the statistic that is X bar. Does the tenant group have significant evidence at the alpha level of 0.05 that the new development is false advertising? All right. The population here is several thousand apartments. Okay. The parameter we're looking for is mu, which is the mean square footage of a single apartment in this development. The general equation, this is on your cheat sheet. Okay. Um, we're going to get the test statistic. Now, one little clarification here. Um, if you know sigma, then technically you would use sigma here, okay? Um, but for the purposes of this homework and just where we're at in the chapter, I'm going to proceed by using S sub x and carry it out because there's a lot to learn from this. But technically, if we do know sigma, this would become sigma, okay? And then if you actually know sigma, this is not any longer a t-distribution. It would actually be, you would not get a t-star. You would not have degrees of freedom. Um, but I don't want to go down that road. I'm going to treat it like like a t-test with a sample standard deviation because this is by far what you're going to see on the exam in May. So, state, mu, we just did that above. X bar, that was the 1240 that I highlighted a moment ago in orange. The sample result was 1240 square feet. The null, I highlighted that. That's what they're advertising. They're advertising that mu is 1250 square feet. The alternative hypothesis is, look here, it said that this group thinks they're smaller than they are advertising. So mu would be less than 1250 square feet. And the alpha that they gave us was 0.05. So that's your state. Plan, name what we're doing, one sample t-test. And again, we're treating it like a t-test. Conditions, was it random? We actually have a bit of a problem. It just said sample. It did not state that it was random. So, uh-oh. You might be like, good, I don't have to do the rest. Haha, just kidding. Just say proceed with caution. Exclamation mark. What? Okay. Number two, the CLT. We do a CLT when we have sample means. The sample size was 150, so we cleared that hurdle. I would state 150 is greater than 30, right? Check. And then I would say, so the three dots means therefore it is approximately normal. So check. Number three, is this considered to be independent samplings? The 10% rule simply says take your sample size and multiply it by 10 and then compare that to the population. So 10 times 150 is 1500. That is less than the population of all the apartments because it said the population was several thousand. So this is not several thousand, okay? So we satisfied all three conditions. Let's do the work now. Our test statistic using this formula, let's put the pieces together, would be 1240 minus 1250 divided by this. What did they give me? The standard deviation I'm using is 38. That's what I'm using for right there. 38 divided by the square root of the sample size. And that'll be my test statistic. Take a minute on your calculator and do that, and you should be getting negative 3.22. Okay. Degrees of freedom is n minus 1, so 43 minus 1 is 42. So on my picture here, I like the pictures, it always helps me. 1250 is the center of this sampling distribution if they are advertising truthfully. Our sample is over here at 1240. In fact, I can tell it's going to be probably further over here because I can tell that because this is a pretty large negative z-score. It's quite a ways over there. And then we're trying to find this shaded area right there. Okay. If we just use the calculator, it can do it for us. We're going to go to the Stat menu, then the Tests button, and it's number 1, a one sample t-test. Really quickly, right above it, you can see it says z-test, one sample z-test. Technically, up here, because we were told sigma, truthfully, it's probably a z-test, but we're doing a t-test, and just to know that the difference in the results on these two is going to be extremely negligible. It's going to be very tiny. But I want to do a t-test for the purposes of where we're at. So number 2, one sample t-test. I've already entered the information. You can see it's there. S sub x is the 38, even though in reality it is sigma. And then it gives you the test statistic. There it is. It matches negative 3.22. And the p-value. So this shaded area, it's telling us, is 7.7. This shaded area right here. Well, let's see, right at 7.79 times 10 to the negative 4 would be 0.000779. So it's pretty much not gonna happen. Now, let me also just show you how would you do this on the green packet. You would look this up in table B because it's a t distribution. That's how we're treating it. And we're going to look up the 42 degrees of freedom and our test statistic. Okay, let me see, where did I put that? Here. So again, table B, t distributions. Degrees of freedom was 43, but remember you go up to the smaller number because you're going to have a more conservative estimate this way. So I've highlighted that row. And what you're looking for as you scan the row is where in here is my test statistic. Remember, it was, I already forgot it. It was negative, oh, negative 3.22, right? Yeah, yep, right there. Okay. Fag, here we go. Negative 3.22. Now, one other thing real quick. These are all positive, right? You notice these are all positive? Um, so the curve is treating all these as if they were positive t's, but there's symmetry, right? So, if this was 3.22, then it would match and have symmetry with negative 3.22. These two shaded sections would be the same size. Negative 3.22, it falls between these two numbers. Well, on the positive side, like 3.22 is in here somewhere, right? So then what you're going to do is you're going to say, oh, okay, well, I'm coming up here for both of these, and this is the p-value is listed across the top here, okay? These numbers right here are the p-values. Now, when you use the packet, you're not going to get a precise value like you did with the calculator. But what you can say is, okay, well, I've got this and this, and it's telling me that the answer is in between those two, okay? So it's the best I would be able to say from the packet alone is that P is in between these two decimals like this, okay? Like that. And I believe it was because the calculator gave us what? The calculator gave us that decimal right there that we wrote down. It gave us 0.00 0779. Well, interesting. I guess it's really, it looks to me like it's actually over one spot. It's between these two. Um, but the difference is quite negligible. I think what the difference is from is that here we're limited with our degrees of freedom. We can only, the degrees of freedom is technically 43. So here we dropped to 40 because that's the best we could do, which I think shifted us a little bit over here. And we are just kind of over one little level and one column, I should say. But this is how you would do it if you were only using the packet. And either way, we're going to have the same conclusion, okay? The conclusion with such a small p-value is we're going to reject the null, right? With p less than alpha. And if you're like, what are you talking about, Phi? Because 0.00079 is less than 0.05, right? We will reject the null. The data suggests, the data is convincing or significant, any of those phrases, that what? That the alternative is true. Here's your alternative, that the apartments, the mean square footage of the apartments is less than 1,250 square feet. Okay, types of errors. A type 1 error is when H null is true, but the data leads you to reject H null. Okay, and so that's what we could have done here. We did reject the null, but what if it was true? In context, what does that mean? It means we publish that the apartments are smaller than 1,250 square feet, but they are actually a mean of 1,250. Now, what does that do to the company, right? This has consequences. This defames, I don't know if that's the right word, or slanders the company, right? They're going to get a bad reputation, wrongfully so. Okay, they might sue you. Um, and in this chart, okay, type 1 error happens in this box. You rejected the null, but the null was actually true right there. Okay, type 2 error is this box when you rejected the alternative. Okay, type 2 error is when the alternative is actually true, but the data leads us um, to fail to reject the null. Okay, we, in other words, we said, yeah, the data looks like the null could be true, but in reality, the alternative is true. And so, what would that mean for the apartments? This isn't what we concluded, but hypothetically, if you did a question, what would that look like if you made a type 1 error? Um, it would mean we conclude we would fail to reject, right? We conclude the apartments have a mean of 1,250 square feet, but the alternative is true, which the alternative is that they're too small, but they actually have less square footage. Okay, and what's the consequence to this? Tenants will feel tricked or misled, and they will not have as much square footage in their apartments as they're expecting to. Okay. Couple new thoughts here. Um, the power of a test is the probability of correctly rejecting the null hypothesis. Okay. The power is the um, probability of correctly rejecting the null. This is not something your calculator can tell you. Okay. Um, it's a much more conceptual. The power can be increased in two ways. If you take a larger sample, you're going to increase the probability of correctly rejecting the null. In other words, um, not making a type 1 error. And number two, if you lower alpha, it's going to make the probability of rejecting the null lower. And if the probability of rejecting the null is lower, then this probability is going up. Okay. Would the power be high or low in this case in particular? Okay. When you get such a such a small test statistic that's way out here, you feel like you're pretty good here. Like, I feel like I am correctly rejecting the null. The probability of being correct in the rejection is really, really high. So this is a bit subjective here. You're not going to be finding this number anywhere in your packet. You're not going to find it anywhere in the calculator. take a guesstimate of the power. Well, I'm feeling pretty good that I'm correctly rejecting the null, so I don't know, say I'm 99, it's a probability, right? Like 99% that I'm correctly rejecting it. Um, if I was getting a test statistic a little over here, that led me to say a p-value. This p-value is tiny, so I'm feeling really confident in it, okay? But what if I got a p-value of like, I don't know, point oh 0.03? Well, that I don't feel strong about. The probability of a type 1 error is alpha, okay? Um, and the probability of a type 2 error, this one's harder to wrap your mind around. So in this chart here, right? This is alpha, the probability of a type 2 error, okay? Then what's the probability of a type 1 error? Here, we have probability of a type 2 error. This column, these two events are complementary, meaning this and this, the probabilities add up to 100. And here, this column is also complementary. If you are okay, let's just throw numbers out here. So let's say this was 95% and this was 5%. They have to add up to 100, okay? And in this case, alpha would be 5%. And the same thing goes over here, okay? So the probability of a type 2 error is, I wrote it down here. The probability of correctly rejecting the null, okay, is the power. And that would be this, right? This box. You are okay. You rejected the null, and you should have rejected the null, okay? This is the power. So I'm going to put, this is the power in this box, okay? The power and the type 2 error are complements. So this plus this must be 1, okay? So let me just give a generic, let's say this is x, right? So x plus the power equals 1. And I want to find the probability of this. So it's 1 minus the power, okay? 1 minus the power. Because this, again, this first part is the power. And what I'm trying to say here is that these two things are complements. The probability of a type 2 error. If you don't make a type 2 error, then you are correctly rejecting the null, which is what these two are here. Type 2 error, the complement of it is correctly rejecting the null. All right, very conceptual there. All right, moving on. Number 2. This is about spindles at the Ford Motor Company. They're supposed to be 5 millimeters. There's that word supposed to, so this is the claim. So this is my mu, okay? And once again, like the one above it, they are giving me sigma, okay? And I am going to, again, I'm treating this as a t-test. I'm going to use sigma I'm going to use that for the s of x right there, okay? And I got my mu right there is going to be the orange one. The x bar, if I keep reading, that's going to be, they took a sample and they found the average to be 5.04. So that's my x bar, okay? This is x bar. My sample size, keep reading as we go. Sample size was 43. So that's my n, okay? And the alpha level is 0.01. So the population is all the spindles that this company, the Ford company, has ever made, and they make millions of cars. The parameter is mu. It's the average diameter of a spindle in millimeters. Um, State your plan. Mu is right there. X bar, we went through and found X bar is 5.04 millimeters in blue. The null is in orange. It's what it's supposed to be. It's what they're claiming. So mu is 5 millimeters. The alternative, I'm looking at this. I'm looking for guidance. Is mu going to be less than, greater than, not equal to? The average is larger than 5. Does the manufacturer have significant evidence that the shipment is defective? I'm going to let the sample guide me to do a greater than here. Greater than 5 millimeters. There's nothing in the wording to lead me to say not equal to is what I was looking for. And alpha is 0.01. Name the test. Random. This was like the one before. It did not say random. So, we'll proceed with caution. CLT, I think we're going to get there. The sample size was 43, which is big enough. So again, ... it's approximately normal. Independent. Take your 43, multiply it by 10, you get 430. They have made millions of spindles, so that is way less than the population. So it's okay. I've got independence. All right. My T is going to be 5.04 minus 5 over the standard deviation. That's 0.04 in pink there over the square root of 43. And I'm getting a really, really large statistic of 655. Wow, it's huge. Degrees of freedom is going to be, 43 minus 1, which is 42. I just realized I made a mistake on all of this. I apologize. I was using the wrong one. This one had a sample size of 150. My goodness gracious, that makes so much more sense. And I was making an explanation. I was explaining it away. Oh, let's circle back quick. Hope you don't mind. So this is going to make the table give us the correct p-value. Hold on. Sorry, and you probably gave up watching the video. So what it's going to do, essentially, it's going to take all of this that I have here, and it's going to shift it all over to here and down to 100. Okay, so I guess these two come up here, but it does work because my sample size was 150, right? So you go to the next size down. So it'd be 100 that you're looking at all the way across. And then 3.22, to remind you, is what I was looking for. So it actually does match up with the calculator. So look at me, silly me. Just wanted to clear that up. Okay. This time, I am going to be looking at this row, though. I am actually going to be looking at the 40 for my test statistic. Okay. And this time, I got 6.55. And if you look here, the test statistic is here. It's getting larger, and I never see 6.55. In fact, 6.55 is off the edge, right? 6.55 is that away, quite a ways. So if I look up here, that means, let me get rid of the old ones. That means my p-value is that away, because that's where 6.55 is, right? The p-value is these across the top. So as you go this way across the top, what's happening to your p-value? 15, 10, 5, 2.5, 2, 1. It's getting smaller. So the best I can say this time is that my p-value is smaller than 0.0005. P is less than 0.0005. which essentially means my p-value is going to be practically zero. Okay, um, back to here. All right, um, my so if I were to sketch this, right, 5 is the middle of the curve. My sample is way over here at 5.04, which has a test statistic of 6.55. This shaded area is going to be practically zero. Let's see what the calculator says it is. Mu is 5. Sorry, start over. Stat, tests, t-test, number 2. Mu is 5. X bar is 5.04. There were 43, wait, that's the sample size, 5. The standard deviation was 0.04. Sample size was 43. And we did a greater than test. So make sure you see the options here. You have the same thing on your calculator, maybe a slightly different format. But there's my t of 6.55, and sure enough, look at the p-value. The calculator is putting it at um, uh, really, really tiny, right? It's putting it at 0.0000. That's 4, 5, 6, 7, and then 8 would be the 3. That's my p-value. Ridiculously low. It's not happening, folks. It is 0. Okay. Um, so with p way less than alpha, we will once again reject the null. The data suggests the mean spindle size is larger than 5 millimeters. Okay, based on what they did, what kind of mistake could they have made? Well, when you reject the null, but the null is actually true, that's a type 1 error. Okay, type 1 error. And what are the consequences of this? This would be bad for the Ford company, right? They might have to redo their manufacturing line. People might be untrusting of their cars now, and they might stop buying them. Um, let's say, they may pay to fix a problem that it doesn't even exist. Um, let's just leave it at that. Or the publicity would be bad. You could say that too. Bad publicity when it leaks. Would the power be high or low? Again, well, when you get such a tiny p-value, it is very high. So you could say 98%, 99%. You might even say, shoot, this is so high, I'm pretty darn confident. It might be 100%. The probability of a type 1 error is alpha. So in this case, that was a 1% chance. The probability of a type 2 error is 1 minus the power. You can refer up higher on the notes for that. So let's say you did 99. Well, whoa, 5, you're getting tired. 1 minus 0.99. The probability of a type 2 error would also be 1. So I'm just grabbing the 99 because that's the power. Okay. So thank you. That was lengthy. You guys are the best.